Okay, so now let's use these rules to actually derive or prove some theorems. So here's our first theorem in logic. This is going to be a very easy one. We'll say that false or false is actually equal to false. Okay, so how does the proof look like? Now remember, all of our proofs work by doing writing the left-hand side equal and continue until we get to the end. So let's do that. We'll write the left-hand side, which is false or false, and now we'll have a chain of equalities. And actually, our first equality is just simply going to say false. This is the end of the theorem. This is the entire proof, and we have to give a reason, and the reason we'll give is OR identity. Now, OR identity is actually the rule that says X or false is equal to X. And if we simply say that X is really false in this rule, then you notice that we get precisely the theorem that we're trying to prove. So it's just a one-liner is as easy as it gets. Okay, so let's try a different theorem. Okay, and let's do instead false or true. So we have false or true, and we believe that that should be equal to true. So let's see if we can prove this. Well, we'll write the left-hand side, false or true. That's how we do all of our theorems. And again, in this case, this is a very easy theorem. We'll just immediately get the answer. And this time what we're doing is we're using the rule OR null. And just so you recall, OR null says X or true is equal to true. Okay, so if we simply set X to false, then we get the theorem immediately. It's just one step. Again, as easy as it gets. Okay, so let's try another theorem. This time we'll say that true or false is equal to true. Now again, for the proof, we'll start with the left-hand side. That's just true or false. And one more time, we're going to be able to just immediately get the entire theorem. And this time the rationale is going to be OR identity. And OR identity is a rule that simply says X or false is equal to X. In fact, we already used this. Okay. But this time what we need to do is set X to true, and we get a result. So it's very, very, very easy. I promise you they're going to get a lot more interesting. But there's only one left that kind of looks like this. So let's go ahead and do it. And so now our theorem is true or true is equal to true. Okay. And the proof, again, is going to be a one-liner. We just write the left-hand side, and we can immediately go to the conclusion. Okay. And the reason for that is OR null. And again, OR null is the rule that says X or true is simply equal to true. So all we need to do is set X equal to true, and we say, oh yeah, that's the theorem. So we're done. Okay. Now we basically looked up 4 different theorems combined, and we can write them like this. This is kind of the common way of writing this, and it's called a truth table. And what you have is you have a column for X, okay, right here, and then you have a column for Y. These are all the possible values of X and Y together. If you had another proposition, Z, then you would have 3 columns for X, Y, and Z. I like to list them in this order. So first I say false, false, and then I say the first variable stays at false, and the second one will change to true. I've run out of possibilities, so then I change the first variable to true, and then I go through false, true in the second and third. Another way to think about it, if you're come from a computer science background, is 0 is false, 1 is true, and so I'm basically listing them in increasing order. Okay, so that's how I always enumerate, if you will, all the rows in this truth table. Now the last part of the truth table is this column here, and that is the actual answer. Okay, so this is the output, if you will. These are the inputs. And that tells us what the value of X or Y is. And we talked about this in the very beginning, kind of intuitively that x or y was false only when both x and y are false, and you can see that directly in this truth table. But this is more than that. This is not kind of an understanding between us. This is a bona fide theorem. It's a simple theorem, but it's actually a theorem. It says from the axioms that we developed at the beginning, or we accepted at the beginning, this is inescapable. This is simply a fact.